Welcome to EDU World Space.
This is a good example of a work energy problem where we have to use the work energy theorem to solve part A, and then work is the change in energy in part B. So I listed out what I know, and then I drew out a description of what was happening just to organize my thoughts. So the mass here is 0.2 kilograms. That was given in the problem, as well as the radius of the curve, which is 1.6. Since it's a quarter radius, that's actually going to be the change in height that we use from A to B. It's going to be the change in height, 1.6. Velocity at B is 4.8 meters per second. So there is going to be some loss here of energy from where we started to B. And then the rest of that energy is going to get lost from going from B to C over 3 meters. So I put down that as well, that I have no velocity left by the time it reaches point C. We want to know what the kinetic energy's coefficient is. Kinetic coefficient friction. So part A, we're going to use the work energy theorem. Work is the change in energy. We know that work is F times D here, and the F, the force that's causing the change in energy, is the friction force from B to C. So I plugged in mu times mass times gravity times the distance traveled. And the change in energy is all in the kinetic energy. It's going to go from having an amount of kinetic energy, 1/2 mvb squared, and it ends up with none. So this was actually a negative value. I dropped off the negatives because the force is also negative. It's to the left, so the negative signs dropped off. So if I rearrange everything, I can first cancel out mass, and then I rearrange everything. I get mu is going to equal the velocity at B squared divided by 2 times g times the distance traveled for this to come to a stop. So plugging in the numbers, we get 4.8 squared divided by 2 times 9.8 times 3, and we get 0.392 is the coefficient of kinetic friction. So part B is on the same line of thought. Work is equal to the change in energy. This time we just need to figure out what the work is done because that force of friction is actually a varying force because the normal force is changing at every moment. So we aren't going to use F times D and figure out what the coefficient, because the coefficient may be equal to what it was before if this is the same surface, but the normal force is constantly changing because of our angle change. So the change in energy here, we can look at, well, what did we have to end with? It was all in the kinetic energy. We're at the lowest point of the travel, and so we could put in the kinetic energy is equal to 1/2 mv squared, where the v is the velocity at point B. Where was all the energy to start with? It was at point A, and it was at rest at that moment, and it was at its highest point. So we can use mass times gravity times the height at A as our initial amount of energy. So final energy is all in the kinetic, initial energy was all in the gravitational potential. Plug all the numbers in, and we get a negative 0.83 joules. Why are we getting a negative? Because there was amount of work lost, or amount of energy lost. So there was a negative work done, which makes sense because this is friction doing the work. It's always going to take away from the system. I hope that was helpful.